You are standing in a supermarket on an unremarkable Tuesday afternoon. You are holding a jar of the wrong brand of pasta sauce, and you are fine. You are fine in the way that most people who are grieving are fine most of the time. Upright, functional, oriented in space and time, making small decisions between tomato products. And then something happens. The sound system plays a song you hadn't consciously thought about in years. Or you notice a man 2 aisles over with the same particular way of carrying his shoulders. Or the light through the window falls on the floor tile at an angle you cannot name, and then you are not fine at all. The jar goes back on the shelf because your hands have started to shake, and something behind your eyes has begun to push, and you cannot locate the reason. You are not thinking about them. You are thinking about dinner. This is one of the most disorienting features of grief, and it is also one of the most precisely measurable. The random moment, the ambushing, chemically inconvenient episode that arrives in parking lots and grocery stores, and the third minute of a phone call about something entirely unrelated, is not a failure of emotional control. It is a biological event with a mechanism, and the mechanism explains something larger. Why grief does not proceed in a straight line from loss toward equilibrium, but instead accumulates in the background of ordinary days and discharges itself in places you would never have chosen. In 1994, a biochemist named Dr. William Fry II, working at Ramsey Medical Center in St. Paul, Minnesota, published findings that changed how the scientific community thinks about emotional tears. He had spent years collecting actual chemical samples of human tears under controlled laboratory conditions, and discovered something that challenged the assumption that crying is merely mechanical drainage. Emotional tears have a measurably different chemical composition than the tears your eyes produce reflexively when you slice an onion or walk into wind. Reflex tears are essentially a cleaning solution: water, sodium chloride, a thin lipid film. Emotional tears contain something else. They carry elevated concentrations of adrenocorticotropic hormone, a central signal in the body's stress response cascade. They carry leucine and enkephalin, an endogenous opioid your body manufactures internally to modulate pain. And they carry, at concentrations significantly higher than anything found in reflex tears, a hormone called prolactin. Prolactin is classified primarily as a reproductive hormone. Its most documented function is promoting milk production after birth. Its presence in emotional tears seemed, at first, like an odd detour. But prolactin's role in emotional crying is now understood to be central. Women have approximately 60% more prolactin receptors in the lacrimal glands than men do. This is why adult women cry, on average, roughly 4 to 5 times more frequently per month than adult men. Not because of any difference in emotional intensity, but because the receiving tissue is biochemically more sensitive to the signal. The threshold for the lacrimal discharge event is structurally lower. But here is the finding that matters for the random moment in the supermarket. Prolactin accumulates. There is a book called What Feynman Knew About Grief that maps the precise science of how we carry loss, including the chemistry we are discussing right now. It is linked in the pinned comment below, and it is only available while this video is running. If the random ambush has been part of your experience, the book asks the question you may have been carrying. Not why you cry, but what your body is doing when it does. The link is below. To understand why the supermarket moment happens, you have to understand what your body is doing on all the days it does not happen. When someone dies, when the person your nervous system has organized itself around is permanently absent from your available world, your hypothalamic pituitary adrenal axis enters a state of sustained low-level activation. The HPA axis is the body's primary stress regulation circuit, running from the hypothalamus through the pituitary gland to the adrenal glands above your kidneys, governing the timed release of cortisol. In ordinary circumstances, it operates in a regulated daily cycle. Cortisol peaks in the morning, tapers through the afternoon, drops during sleep. A rhythm called diurnal variation. Grief disrupts it. Dr. Mary Frances O'Connor, a cognitive neuroscientist at the University of Arizona, who has published peer-reviewed research on the hormonal signatures of bereavement for over 15 years, documented in multiple studies that bereaved individuals show measurably flattened cortisol curves. In a paper published in Psychoneuroendocrinology, O'Connor and colleagues found that participants who had lost a spouse or child within the prior 14 months showed significantly dysregulated cortisol patterns compared to non-bereaved controls, and that this dysregulation correlated directly with the severity of intrusive grief symptoms, including sudden, unexpected emotional episodes. What this means at the level of your physiology is that your body is running a sustained background stress signal on the ordinary Tuesday of the pasta sauce. The HPA axis is not in crisis. It is in low-level chronic activation, the physiological equivalent of an alarm held just beneath the audible threshold. Cortisol is present at the wrong times of day. You feel experientially fine. The signal is below consciousness, but the signal is there. Researchers at the Karolinska Institute in Stockholm documented that HPA axis dysregulation of this kind persists not for weeks, but for months after major loss, extending across years in a significant subset of bereaved individuals. The body holds a residual activation pattern in the circuitry long after the acute phase has passed. Now consider the prolactin. In a bereaved individual with a dysregulated HPA axis, prolactin production by the anterior pituitary remains elevated. Day by day, across the ordinary days of work and meals and adequate sleep, the hormone accumulates in circulation. The lacrimal glands are prolactin-sensitive tissue. They are waiting, in the most mechanistic sense of that word, for the signal to reach threshold. Imagine the structure as a reservoir. The reservoir has an inlet, the ongoing stress hormone production, the daily prolactin output, the HPA signal, running quietly below the surface of your functioning days. The reservoir has an outlet, the lacrimal discharge event. When you do not cry for several consecutive days, the reservoir fills. The outlet does not open because no incoming signal has reached the required threshold. The inlet continues, the level rises, and as the level rises, the threshold required to force the outlet open decreases proportionally. This is why the specific trigger is, in one precise sense, almost irrelevant. It is not that the song was uniquely powerful. It is that the song arrived at the moment when the reservoir had reached capacity. Any signal of sufficient amygdala weight would have served. The song got there first. Ad Vingerhoots, a clinical psychologist at Tilburg University who has published more peer-reviewed research on adult crying than perhaps any other scientist alive, described this as a pressure regulation model. Vingerhoots documented across multiple study populations that crying frequency in bereaved individuals follows a pattern consistent with accumulation and discharge rather than direct stimulus response. People do not cry in direct proportion to how much they are consciously thinking about the person who died. They cry in proportion to how long it has been since they last did. The randomness is not random, it is hydraulic. If you are watching this because someone in your life is carrying this, the ambush in ordinary places, the inexplicable timing. What Feynman knew about grief is in the pinned comment below, available only while this video is running. The amygdala is an almond-shaped structure, roughly 1 cubic centimetre in each hemisphere, buried deep in the medial temporal lobe. Not the seat of sadness in the conversational sense, but a rapid assessment system that evaluates incoming sensory data for significance and initiates autonomic responses before the prefrontal cortex has time to reason about what it is perceiving. It receives direct projections from the olfactory system and from the auditory thalamus along pathways that bypass the neocortex entirely. The smell of a specific jacket, the first 4 notes of a song. These reach the amygdala before they reach the reasoning brain. The amygdala processes them against its encoded library of significance. Memories tagged during high arousal states, including the period of the loss and the months surrounding it. And if they match, it fires. The autonomic cascade begins before you know why. Dr. Naomi Eisenberger, a social neuroscience researcher at UCLA, published work in Science demonstrating through functional magnetic resonance imaging that the neural signature of social loss activates the same anterior cingulate cortex regions that register physical pain, replicated across multiple studies following her 2003 paper. Social pain is not metaphorical, it is processed by overlapping circuitry with the same tissue that signals physical injury. When the amygdala fires a significance flag on a sensory cue associated with the person who died, What follows is measurably closer to a pain signal than a feeling. But the pain signal does not deliver its own explanation. It produces only its physiological effects. Increased heart rate, altered respiration, the vagus nerve sending parasympathetic signals along its fibers running beside the larynx and into the chest. While the prefrontal cortex catches up and attaches a name to what is already happening by then, the lacrimal reflex has often already initiated. The lacrimal glands sit above the outer corner of each eye, behind the brow ridge. They are governed by the autonomic nervous system through the parasympathetic fibers of the facial nerve. When the limbic system reaches a certain activation threshold, the hypothalamus signals the lacrimal glands, which begin producing fluid at a rate that exceeds the drainage capacity of the nasolacrimal duct. The fluid reaches the lower eyelid margin and overflows. This is not a decision. It is fluid dynamics, governed by nerve signals, governed by a threshold your body reached before your prefrontal cortex filed any paperwork. There is a further dimension to the precise timing. The prefrontal cortex, which governs executive function and the active suppression of subcortical emotional processing, is a metabolically expensive system that fatigues across a normal day of demands. During sustained attention, a work meeting, a focused task, it maintains top-down inhibition, a continuous signal that keeps subcortical emotional processing subordinate to goal-directed behaviour. When it releases its grip in the parking lot after a long afternoon, in the third minute of the drive home, the inhibition lifts, the amygdala, running its significance matching against a full reservoir, finds its threshold has dropped. This is why the grocery store and not the meeting room. This is why Tuesday afternoon and not Tuesday morning. The suppression system ran out of fuel. The reservoir found its outlet. The answer is in what the tears contain. Emotional tears carry leucine and enkephalin, endogenous opioids your central nervous system manufactures in response to pain and stress signals. They bind to the same receptor class as morphine, though with lower affinity and shorter duration. Their presence in emotional tears indicates they are simultaneously elevated in the blood and central nervous system during and after a crying episode. The discharge event is not merely draining a reservoir, it is triggering the release of the body's own pain-modulating compounds in direct response to the pain signal that initiated the event. The amygdala fires, the cascade begins, the discharge occurs, and embedded within the discharge is the release of enkephalins that blunt, temporarily, the signal that caused the discharge. The body is running a self-contained regulatory loop. Detect the overload, initiate discharge, release analgesic compounds during discharge, return provisionally to baseline. From the outside, this looks like falling apart. What it is, at the level of the chemistry, is a regulated pressure relief cycle with a built-in analgesic component, a 2014 meta-analysis published in Emotion by Jonathan Rottenberg and colleagues, drawing on data from over 400 participants, found that crying in response to grief and social loss was followed by measurable mood improvement in approximately 58% of cases within 30 minutes of the episode. Grief-triggered crying in the presence of minimal social safety consistently activated the mood recovery pathway via enkephalin release, autonomic rebound from sympathetic to parasympathetic dominance, and the prefrontal cortex's successful labeling of the trigger source, which restores top-down inhibition once the signal has been named. The crying episode is not the symptom you manage. It is the mechanism by which the regulatory system returns itself to a state capable of functioning. What Feynman knew about grief maps this specific mechanism, the chemistry of what happens in your body during and after the episode, and what the data says about why the random moment is not instability, but a regulatory system doing exactly what it was built to do. The book is in the pinned comment, only available while this video is running. There is a final layer. The sensory cues that fire the amygdala were encoded during the highest arousal period of your recent history. Memory consolidation research, including James McGaw's foundational work at the University of California, Irvine, established that memories formed during intense emotional arousal are encoded with greater specificity and more robust retrieval architecture than ordinary memories. The amygdala releases norepinephrine during high arousal states, and norepinephrine acts on hippocampal circuits to enhance the precision of the memory trace being formed in real time. This means that the sensory landscape of the week surrounding the loss, the quality of light in a hospital waiting room, the pitch of a phone call that arrived with news, the smell of a room, the sound of a footfall in a hallway, is encoded with extraordinary precision and multiple redundant retrieval pathways. And because the amygdala processes sensory data before the cortex does, these encoded memories become triggers that activate faster than recognition, faster than naming, faster than the capacity to prepare. The triggers are everywhere because the encoding was thorough. Your brain did not make an error. It preserved the sensory coordinates of the highest significance period of your experience with maximum fidelity. For a future it assumed would need that information. What it could not have anticipated is that the stimuli it encoded with such care would persist intact in the ordinary world long after the person who gave them their significance was no longer in it. Gone from reach and gone from existence are not the same thing. Your nervous system was built on that distinction. It knew someone as a set of sensory coordinates. A sound, a smell, a particular weight in a room, a quality of presence registered by the body before the mind named it. Those coordinates do not disappear from the archive when the person is no longer present to match them. The world keeps offering partial matches, close enough to trigger the signal, not close enough to satisfy it. You are standing in a supermarket. You are holding a jar of pasta sauce. You are fine in the way that a sealed system under elevated pressure is fine, contained, functional, running measurably hotter in places no instrument was monitoring. The song played. The amygdala found a match in its archive, and the signal it sent was older and larger than the song. The prolactin accumulated across 9 days of ordinary functioning reached the threshold the lacrimal glands were waiting for. The autonomic nervous system sent its signal through the facial nerve. The enkephalins began their release. And in the chemistry of that unremarkable Tuesday, your body ran the only cycle it has for an unresolvable signal. Discharge it. Dull it. Return provisionally to calibration. The jar went back on the shelf. Your hands shook. You cried in a place you would not have chosen. For reasons that had been accumulating since before you walked through the door, the body does not grieve the way a mind does. It runs a series of regulatory mechanisms in response to the permanent removal of a signal. It was organized around receiving. The HPA axis quietly elevated. The prolactin reservoir filling. The amygdala matching fragments of an encoded world to the faces and sounds and light angles of the living present, until the system reaches the threshold that empties it. It reached it in the pasta aisle. If you have been carrying this, the ambush, the inexplicable timing, the chemistry of a grief your body refuses to schedule. What Feynman knew about grief is in the pinned comment below. It maps the science of what your body is actually doing when it does this. It is only available while this video is running. The link is below. Same one. And so is the question the book begins with. Not how do you stop the random moments, but what are they evidence of?